Right now, if you pull up to an electric vehicle charger in the United States, there is basically a 1 in 5 chance that it's completely dead.
Just entirely unresponsive.
Yeah, not slow, dead. And I mean, if you think about it, if 20% of the gas pumps in America were broken today, it would be like a national emergency.
People would be panicking.
Exactly. But for the massive global transition to electric vehicles, a 20% failure rate is, just a regular Tuesday.
Right.
We are so used to the infrastructure of our lives just functioning invisibly in the background. But the expectation of a seamless transition is hitting a very hard, very frustrating reality.
It really is. I mean, we are witnessing the awkward adolescence of a massive infrastructure shift right now.
Yeah.
The vehicle technology, so the battery density, the motor efficiency, is advancing exponentially faster than the physical power grid or even the deployment networks can possibly handle.
It's like the cars are living in the future, right?
Precisely. The hardware inside the cars is living in 2026, while the infrastructure trying to support them is, well, it's stuck trying to catch up.
And for you listening, that is exactly our mission today on this deep dive. We've gathered a really fascinating stack of sources to figure out the mechanisms behind this bottleneck.
Some really diverse sources, too.
Oh, absolutely. We're looking at everything from Harvard Business School research that analyzed millions of driver reviews to European market reports on AFI regulations. We're even digging into the actual technical engineering specs on LFP battery buffers and military-grade mobile chargers.
It's a lot of ground to cover.
It is.
Yeah.
But we're going to unpack why public charging feels so chaotic right now and look at the ingenious, basically grid-hacking ways the industry is rushing to fix it.
Because the narrative has shifted completely from just a few years ago.
Yeah, let's talk about that. The old narrative was always range anxiety, right?
Right. The prevailing fear used to be range anxiety, that psychological dread that your car's battery would simply run out in the middle of a highway.
Like driving on empty.
Exactly. But the data we have now tells a completely different story. Drivers are no longer afraid of their batteries. They are afraid of the chargers themselves.
Which is wild.
It is. The industry refers to this as charge anxiety, and the data entirely backs up that fear.
Okay, let's unpack this because we have that Harvard research from Omar Asensio, and the methodology his team used is just fascinating.
It wasn't just a survey.
No, not at all. They used custom AI to scrape and analyze over 1 million charging station reviews across 72 different languages.
Over an entire decade of data.
Right. And the AI actually parsed the sentiment to find specific failure modes. So things like broken screens, snapped cords, software handshakes that just timed out.
And what did that reveal?
Well, the standout metric from all that data is a 78% reliability score for public chargers in the U.S.
Which is, frankly, staggering. In the world of commercial infrastructure, a 78% reliability rate is catastrophic.
It sounds like a passing grade in high school, but for infrastructure?
Oh, it means out of every 5 charging sessions a driver attempts, 1 fails completely. And that assumes the driver can even figure out what they're paying for the successful session.
Right. The pricing is a whole other nightmare.
The Harvard study highlights that EV charging pricing operates in this completely opaque market. A driver might be charged a flat fee or a per minute rate or, by the kilowatt hour.
And you have no idea until you plug in.
Often not even then. Plus, they frequently need to cycle through, 5 different proprietary apps just to authorize the session.
Yes. There's no giant illuminated sign on the highway broadcasting the price of electricity like there is for unleaded gasoline.
Exactly.
If a traditional gas station operated this way, where 2 out of 10 pumps were permanently out of order and the cashier wouldn't tell you the price of gas until after you finish pumping, people would riot.
They absolutely would.
But beyond the pricing, reviewers in this study were constantly complaining about getting iced.
Right. Ice-eased, meaning internal combustion engine vehicles blocking the EV spots.
Yeah, just a regular gas car parked in front of the charger. Or worse, drivers showing up to a literal charging desert.
Those are geographically fascinating.
Yeah, the research pointed specifically to Ferry County in Washington State and Wise County in Virginia.
Right.
These are regions with average commute times and normal median incomes, but 0 public fast chargers. You cannot functionally own an EV there unless you own a single-family home with a driveway to charge overnight.
And, the federal government actually attempted to address that specific geographical gap.
With the nanny program, right?
Yes. They allocated $4.4 billion for the NEV program. That's the National Electric Vehicle Infrastructure Program. But according to the latest report by the independent electrical contractors, the rollout has severely stalled.
Severely is an understatement. Didn't they only spend a fraction of it?
States have only managed to spend about 2% of those funds.
Wow, 2%.
Yeah. That equates to just $94 million out of the $4.4 billion actually deployed into the ground.
So why is that capital just sitting there? Is it pure bureaucracy?
Well, bureaucratic delays and complex procurement rules definitely play a role, sure. But the primary anchor dragging the program down is the sheer reality of local grid constraints.
Like the power lines can't handle it.
Right. It requires massive utility upgrades before a shovel ever hits the dirt. And the immediate fallout from this sluggish pace is that the federal funding authorized for EV charger installation in 2026 was slashed down to just $300 million.
Oh, wow. So that leaves a massive gap in the public infrastructure we were promised.
It's a huge gap.
So because the government rollout is mired in delays and public infrastructure is highly fragmented, the market is kind of stepping in to force a solution.
Out of sheer necessity.
Exactly. Automakers and drivers are taking matters into their own hands by physically consolidating around the one private network that actually functions reliably.
Which brings us to the definitive end of the plug wars in North America.
Yes, the NACS standard.
Right. For years, non-Tesla vehicles utilized a standard called CCS1. It was this bulky, heavy plug because it used completely separate metallic pins for slow AC charging and fast DC charging.
It was huge.
It was. But over the last couple of years, the industry basically surrendered to Tesla's sleeker design, which shares the pins for both AC and DC.
And that design is now officially standardized.
Yes, as the North American Charging Standard, or NACS, technically designated as SAE J3400.
The scale of Tesla's dominance forcing this shift is just staggering to me. In the U.S., Tesla operates roughly 37,000 DC fast charging ports.
Which is huge.
It accounts for 52% of all the fast chargers in the entire country. Like, over Thanksgiving of 2025 alone, they successfully handled a record 2 million charging sessions in just 5 days.
And that reliability is why everyone is switching.
Exactly. If you look at an automaker like Porsche, their 2026 Macan and Taycan models in North America now come with a native NACS port built right into the quarter panel.
Finally native.
Right. But if you own a 2025 or older model, you have the old CCS port.
Really?
So thousands of drivers right now are relying on third-party physical adapters to access that supercharger network.
Which is, from an engineering standpoint, incredibly risky. Pushing high-voltage electricity through an aftermarket middleman piece of plastic is a severe engineering challenge.
Because of the heat?
But primarily the heat, yes. When we talk about high-power fast charging, we are dealing with 250 to 350 kilowatts of power. That generates a tremendous amount of thermal energy.
Right.
Every physical connection point in an electrical circuit inherently adds resistance. So introducing an adapter between the charging cable and the vehicle's native port adds another physical interface.
A potential bottleneck.
Exactly. If the manufacturing tolerances on that adapter aren't microscopic, or, say, if the metallic contacts get worn from daily use, heat builds up exponentially at that juncture.
And what happens when it gets too hot? Does it just melt?
Well, the charger software will usually detect this thermal spike and derate the session, meaning it slows the charging speed down to a crawl to prevent the plastic from literally melting.
Wow. So the native port is clearly the only long-term solution here, making this whole adapter phase a very messy temporary bridge.
Very messy.
Here's where it gets really interesting, though. This is exactly like the early days of smartphones when every brand had a different proprietary charger, and now we're finally settling on USB-C.
That's a great analogy.
Right. But this standard consolidation is very much a North American phenomenon.
Mm-hmm.
Our sources show Europe is operating in a completely different paradigm right now.
Yes, Europe avoids the specific hardware fragmentation entirely, not because they have better engineers, but because of a heavy-handed regulatory approach.
They just laid down the law.
They did. They mandated a slightly different plug, CCS2, across the board years ago. Furthermore, they are aggressively pushing the AFIR regulation. That's the Alternative Fuels Infrastructure regulation.
What does that do?
Well, AFER legally outlaws the app juggling madness we discussed earlier. It mandates that any new public charger must accept ad hoc payments.
Meaning I can just use my regular credit card.
Yes, a simple, anonymous tap of a standard credit card. It also enforces strict pricing transparency rules.
So no more guessing the price per kilowatt.
Exactly. The U.S. is essentially letting a private market leader dictate the hardware standard organically, while Europe is utilizing federal policy to force interoperability and consumer protection from the top down.
Now, since we are discussing policy mechanics, our sources note the U.S. did make a massive shift in how it incentivizes the vehicles themselves under the new OBBA framework.
Right, the financial incentives.
Yeah, we moved away from the old federal EV tax credit at the point of sale, replacing it with an auto loan interest deduction of up to $10,000 for U.S. assembled vehicles.
And staying objective on the politics of it, the underlying economics of that policy shift fundamentally alter buyer psychology.
How so?
An upfront tax credit primarily incentivizes consumers who already have the capital to buy the car and the tax liability to absorb the credit.
Right, wealthy early adopters.
Exactly. By pivoting to an auto loan interest deduction, the policy targets monthly cash flow instead.
Ah, I see.
It shifts the economic benefit from a one-time discount to a long-term financing advantage. The goal there is attempting to pull the EV market away from early adopters and integrate it into the middle-class monthly payment financing model.
Which means the day-to-day operating costs, like the price of public charging we were just talking about, become even more critical to a middle-class buyer evaluating that monthly budget.
Absolutely.
But, even if we standardize the plug and mandate transparent pricing and shift the financial incentives, we really only solved the connection problem. We haven't solved the grid problem.
No, we haven't. And that is the invisible wall the entire EV transition is slamming into right now.
Yeah.
The power grid was simply not built to handle spontaneous, hyper-localized surges in energy demand.
Okay, let's look at the Avason guidelines on battery-buffered DC fast chargers, because the realities of commercial installation detailed in this source basically blew my mind.
It's pretty shocking.
If a business owner, say a roadside cafe or a small logistics depot, wants to install just one 150 kilowatt fast charger, they cannot simply wire it into their existing electrical panel.
Not even close. A 150 kilowatt charger draws a staggering amount of instantaneous power.
Right.
In almost every market in 2026, asking the local utility company to upgrade a commercial site to handle that load requires a new medium voltage transformer.
Which takes forever to get.
The administrative and engineering timeline for that upgrade ranges from 12 to 24 months.
2 years.
Yes. And the capital cost just for the utility connection, so the trenching, the transformer, the protection relays, frequently lands between $80,000 and $250,000.
Wow.
And that is before the site owner even purchases the actual charging hardware.
So for a single retail location, that math instantly kills the project.
Dead in the water.
It's like, okay, think of an espresso machine at a busy coffee shop.
Okay.
The grid is just the standard wall outlet slowly heating the internal boiler all morning. But when a rush of customers comes in, the barista pulls a shot using all that stored pressurized energy in seconds.
Right.
You couldn't pull that instantaneous energy straight from the wall without tripping the breaker. And businesses are using battery buffers the exact same way to cheat the grid.
Right. That's a great way to visualize it. They place a massive battery pack between their modest grid connection and the fast charger.
And how does the battery hold up to that?
Well, the mechanics align perfectly, though, with a major caveat. An espresso boiler doesn't care how many times you drain it, but a battery does.
Oh, true.
That is why these systems don't use the standard lithium-ion batteries found inside the cars themselves.
What do they use instead?
They use lithium iron phosphate, or LFP chemistry.
Okay.
LFP batteries are physically heavier and less energy dense, which makes them less ideal for putting inside a moving sports car. But they excel at stationary storage.
Because they don't degrade as fast.
Exactly. They can be deeply discharged and recharged thousands of times a day with very little chemical degradation.
So the utility company trickles power into this LFP battery all day and night at a low, steady rate, say 50 kilowatts.
Right.
Then an EV pulls up, and the battery opens the floodgates, dumping power into the car at a blazing 150 kilowatts.
Bypassing the grid limitation entirely.
There is a real-world example from the Avason data that perfectly illustrates this. A rural highway cafe in Central Europe wanted to offer fast charging, but they were like 40 kilometers in the nearest electrical substation with any spare capacity.
A logistical nightmare.
Yeah. The utility company quoted them 180,000 euros and a 22-month wait time just for the trenching and grid upgrade.
But instead of waiting 2 years, they installed a 150 kilowatt DC charger paired directly with a 215 kilowatt hour LFP battery buffer.
Just hooked it right up.
Yes, they wired it directly into their existing low-power 3-phase service panel. The total installation cost was €94,000.
Half the price.
And the entire system was commissioned and dispensing power in just 11 weeks.
Wait, if they are bypassing the grid upgrades, there's a massive financial loophole here regarding how commercial electricity is billed.
The demand charges.
Yeah. They aren't just saving on installation, they are avoiding demand charges entirely.
Yeah.
Because commercial power bills don't just charge for the total electricity used, they charge a premium fee based on the highest peak power draw for the month.
Correct.
So if a car yanks 150 kilowatts straight from the grid, the demand charge skyrockets.
Yeah.
But with the buffer, the grid only ever sees that slow, steady 50 kilowatt trickle. They're basically doing energy arbitrage on their own parking lot.
Precisely. And the eVason data indicates that avoiding those instantaneous demand spikes can save a site anywhere from $18,000 to $36,000 annually.
That's incredible.
The battery buffer effectively pays for its own capital cost in under 7 years, purely through utility bill savings.
So what does this all mean for high traffic areas? If the battery is just a buffer, what happens if 40 cars show up back-to-back on a holiday weekend? The battery eventually runs out of stored espresso.
It does. It all comes down to the energy balance equation.
Okay, do the math for me.
If the grid is feeding the LFP battery at a constant 50 kilowatts, it supplies roughly 1,080 kilowatt hours of usable energy over a 24-hour period.
Which is how many cars?
That is enough total energy to comfortably provide about 20 cars with a 50 kilowatt hour top-up. So if 40 cars show up in rapid succession, the battery will deplete much faster than the grid can refill it.
And then what? It just shuts down.
No, but once the buffer hits its minimum threshold, the charging speed throttles down to whatever that underlying grid connection can provide.
Which in this case is just 50 kilowatts.
Exactly. Queuing and frustration immediately follow. So battery buffers are incredible architectural workarounds for moderate locations moving under 800 kilowatt hours a day.
But not for massive highway stops.
No. For massive, high-throughput corridor highway stations, site owners simply have to bite the bullet, pay the utility, and wait for the massive grid upgrades.
Okay, so standardizing the physical plug fixes the connection to the car. Implementing battery buffers fixes the 24-month grid delay for retail locations.
Right.
But what if you don't even have 11 weeks to install a battery buffer?
A totally different challenge.
What if you are a commercial delivery fleet, or a remote film set, or the military, and you have a dozen electric vehicles that require high voltage power in the middle of a field tomorrow morning?
In those scenarios, you cut the cord to the grid completely.
Right.
We are tracking a massive boom in the sector of mobile off-grid charging. The industry is beginning to treat charging infrastructure as a highly deployable asset rather than a permanent real estate development project.
The military application of the sources is the clearest example of this. We looked at a company called Exos, which recently demonstrated their charger hub for the U.S. Air Force Global Strike Command down in Bossier City, Louisiana.
A really impressive piece of hardware.
It's wild. This is a fully integrated, towable DC fast charger. There is no trenching concrete on a flight line, no permitting, and no utility company involved.
None at all.
You simply hook it up to a heavy-duty pickup truck, tow it to a remote base, and you immediately have high-power EV charging for electric flight line vehicles.
And, it is not limited to towing giant batteries around either.
Oh, right, the L-Charge system.
Exactly. L-Charge is taking a highly innovative mechanical approach. They modify a Ford 250 or 550 truck and integrate a 60 kilowatt DC fast charger directly into the chassis.
But the power doesn't come from a battery pack.
No. It is generated directly by the truck's engine using a PTO or power takeoff system.
Okay, explain that a bit.
Think about how a fire truck pumps water. It doesn't have a secondary engine just for the water pump. A mechanical gear simply diverts the rotational force from the truck's main engine away from the wheels and sends it directly into a massive onboard generator.
Pushing DC power straight into the stranded EV.
Exactly.
But wait, using a gas-powered truck or a generator burning renewable natural gas to charge an electric vehicle. Isn't that defeating the entire purpose of transitioning a fleet to zero emissions?
On a hyper-localized level, yes, it seems counterproductive.
It sounds like a paradox.
It does. But if we analyze the macro logistics of fleet management, it serves as a critical bridge solution.
How so?
Imagine a municipal delivery fleet looking to purchase 50 electric cargo vans today to drastically cut their urban emissions.
Okay.
The utility company informs them it will take 2 full years to upgrade their depot's electrical grid to charge those vans overnight. Do they delay their zero-emission goals for 2 years while burning diesel in their old vans?
Oh, I see.
Or do they buy the EVs right now and utilize a mobile RNG-powered generator to keep them running while the grid infrastructure catches up?
It unlocks the deployment of the vehicles immediately. You don't have to wait for the perfect grid to start the transition. Plus, the L-Charge system only runs the generator when it is actively engaged with a vehicle, unlike older portable generators that just sit there idling and polluting all day.
Right, it's much more efficient.
And for operations that require absolute zero emissions, there are alternatives out there, right?
Yes. Companies like Nuvera are deploying systems called hydrocharge.
Hydrogen, right?
Yes. These utilize hydrogen fuel cells to generate the electricity completely off-grid, emitting nothing but water vapor.
Amazing.
And then SparkCharge is taking a different route, utilizing mobile battery energy storage systems, or BES, that function like giant power banks you can dispatch to a site.
So the overarching theme here is absolute flexibility. The power is no longer permanently bolted to the ground.
Exactly.
Well, we have covered a massive amount of ground today, diving into the literal nuts and bolts of this transition.
We really have.
To synthesize all of this for you listening, we are finally exiting the Wild West era of public EV charging. The days of showing up to a broken, unreadable charger with 5 different payment apps are slowly ending.
The industry is rapidly maturing out of necessity. We are witnessing a massive consolidation around a single, elegant physical standard with NACS, finally bringing hardware simplicity to the charging port.
Thank goodness.
We are seeing ingenious engineering with LFP battery buffers, allowing businesses to bypass slow, archaic utility grids and engage in energy arbitrage.
Right.
And we are seeing the deployment of mobile charging trucks to bring power directly to fleets, treating energy as a dispatchable service rather than a fixed geographic location.
So the next time you plug in an EV or simply walk past a charging station in a grocery store parking lot, you aren't just looking at a plastic cable and a digital screen.
There's so much more to it.
Yeah. You are looking at the culmination of invisible, high-stakes technological battles, massive utility grid constraints, fierce standardization wars, complex thermal management physics, and intricate software protocols, all functioning rapidly behind the scenes to make that seamless charge possible.
The physical infrastructure is finally developing the intelligence and flexibility required to match the promise of the vehicle technology itself.
Which leaves me with a thought I haven't been able to shake since we started unpacking these mobile off-grid solutions.
Oh.
Yeah, if we are shifting so heavily toward on-demand charging and decentralized battery buffers, will the traditional gas station real estate model eventually become completely obsolete?
That's a fascinating question.
Imagine a near future where you never actually drive to a charging station at all. You simply park at work or the grocery store, and your car autonomously pings a roving robotic battery drone.
Like a mobile power bank on wheels.
Exactly. It navigates the parking lot, finds your car, plugs itself in, and charges you up while you're inside buying groceries.
Yeah.
The infrastructure wouldn't just work invisibly in the background. It would literally hunt you down to serve you.
From a broken, frustrating gas pump to an autonomous robot valet, that would represent a complete reimagining of urban design and retail real estate.
Something to think about the next time you're waiting for a charge. Thanks for joining us on this deep dive. We'll see you next time.